Show the products formed from the acidic dehydration of the following alcohol. So here we have a nice alcohol, a cyclic one, and acidic dehydration means that I'm supposed to be using H3O+. Okay, so the only choice I have is to use water and to use the hydronium ion. That's about it. Okay, you can use H3O+ or you can use H+. Okay, it's okay, you can use either of those two things, no problem. So usually when you have an acidic dehydration, it means you're treating the alcohol with an acid, which means that the alcohol itself is going to be the base. If it's going to be the base, then it's going to pick up a proton. It's going to get protonated. So which means my starting point is always going to be alcohol getting protonated. Okay, so OH2 plus. You can write the oxonium ion a different way if you want to, showing the two bonds with the hydrogen, but it's okay because we're going to have to get rid of this anyway. All right, because now that we have made it into H2O, this is actually going to leave as water, because that was the whole point of getting protonated, is that it's going to leave. Okay, and remember, it's also saying that we have to dehydrate. Dehydrate means getting rid of water. Okay, so how do we get rid of water? You can do this. All right, so here we go with that. And so now we have one carbon and the carbocation right here. Okay, this carbocation is a primary carbocation, and a primary carbocation, of course, is not going to be very stable. So which means it's going to start rearranging, which means you need to start looking at where you can move things. Okay, and remember, again, we've talked about this before, is that you can have an H shift, okay, a hydride shift, you can have a methyl shift, okay, or you can have a phenyl shift. So here we don't have a phenyl, so we don't really have to think about the phenyl shift, okay, but we do have a methyl group. And so let's talk about the shifts, okay, that we can do over here. So I'm going to write this again on the left side so we can see what kind of different compounds we can make from here. So here is the primary carbocation. So when I have a carbocation like this, I am focusing on this carbon and seeing what's attached to it. Okay, so which means that in this case, I don't have any hydrogen attached here. Okay, in this case, I have only a methyl group attached here, which means that I can actually take this methyl group and I can move it over here. So that could be a methyl shift, okay, that I have. On the other hand, the other thing that I have attached on this carbon are going to be these two carbons right here. So I'm going to be able to move those also. Okay, so let's take it one at a time. So if we move the methyl group, okay, here, then what do we get? Okay, so if you move the methyl group here, it means that the carbocation will then get to move over here because of the lack of electrons. Okay, and so here is the methyl group, okay, that has moved, and then here is the carbocation, okay, that has formed. So that is one thing that's possible. And then from then on, we'll go on. I want to finish writing the other one shift also, and then we will see what else we can do. So here we are. For the sake of sanity, we can just take the one carbon down here, because both of the carbons here and here, they're both the same, okay? So I'm just going to focus on this one carbon and see if we can shift that over here. So if you shift that over here, what you're really doing is what we call a ring expansion, okay? So when you do a ring expansion, now this bond is literally going to shift from here to here. Okay, so that's what happens here. So let me go ahead and erase that. Okay, and then we'll write this again. All right, so here we are moving this here. All right, that's what's happening. Or you can just close your eyes. Well, don't close them too long, but you can close your eyes and just pretend or just see this one moving to this side. Okay, so which means what we have now is going to be something like this, and I'll draw it very crudely first, and then we'll see what we can do. So this carbon right here, we still have a bond, okay, on that one. We still have this methyl group coming out, but this is the one that I was moving. Okay, so here is that methyl, and then this one is now going to form a bond over here. So which means now I have 1, 2, 3, 4, 5, 6, 7. Okay, I have a 7-membered ring now because the 6-membered ring actually got expanded. Okay, so which means that I have expanded my ring. The other thing I want to talk about is, of course, where is the carbon shifted? Okay, the carbocation, where has that shifted? So once the carbon shifts from 2 to 1, okay, over here, the carbocation is now going to shift to wherever the bond broke. Okay, so the bond actually broke from this carbon right here. Okay, this is where the bond broke, so the carbon is going to shift here. Okay, or the carbocation, I'm sorry, I don't know why I keep saying carbon. So the carbocation is going to shift there. So which means what? Okay, my carbocation is going to be on the 7th one right here. Okay, so I'm going to go ahead and draw the carbocation out. So the 7-membered ring. All right, and then I have a methyl group on one of the carbons, and that's the carbon that has the carbocation. Okay, so those are the two rearrangements possible, the shifts that I have. So there was no hydride shift. Both of these were going to be the methyl shifts, okay, that we did for this mechanism. So now let's go ahead and finish off the products, because now all we have done right now is rearrangement. And why did we have to do a rearrangement? Because this was a primary carbocation, and primary carbocations, as we know, are not stable at all. Okay, so they will rearrange. So this primary carbocation does not exist anymore. Okay, so now what I have to do is I have to look for my beta hydrogens. So my beta hydrogens for the first one are going to be here and here and here. Okay, those are my 3 beta hydrogens, and I hope you will agree with me that these two hydrogens are the same, which means that I'm looking at 1, 2. That's it. Okay, I'm not going to look at the third one that I drew out. So which means that my products that I'm going to draw out now, I'm going to have 2 of these. So I'll have water picking up 1 proton from here, okay, which will leave its electrons there, which means that this is what I have. And I know, I'm sorry, my mechanisms sometimes get a little messy, but there we are. Okay, I'm going to try the structure smaller. And then in the second one, I'm going to have a water pick up this proton right here, and again the proton is going to go away, leaving its electrons towards the carbocation. So now I have this. Okay, so I get 2 different alkenes. Okay, and in these 2 alkenes, the major one is going to be the one that is more substituted alkene. So this is the major product. Okay, whereas this is the minor. All right. Okay, so here let's go ahead and look at the second one that we have. And in the second one, the carbocation is here. I have a hydrogen here, and I have a hydrogen here, and a beta hydrogen here. And again, you will agree with me that these two are going to be exactly the same, which means we have 1 and 2. Okay, so I'm going to go ahead and draw out my 2 dehydrated products, okay, or 2 alkenes that we are going to form. So here is the water picking up this proton is leaving, and so then remember, this is a 7-membered ring. These are a little bit not hard to draw, but still a little bit different. Okay, so there's the alkene, and in the second case we're going to have the water pick up this proton, and this proton is going to leave with its electrons in the ring. So this will give us this. Okay, so again, we still have a 7-membered ring. Now within these two, which one is going to be the major? This is going to be the major because this is the more stable ring, okay, or the more stable, I should say, alkene, not ring, more stable alkene. So this is a Zaitsev product. This is going to be the minor product. Now let's look at one more thing, okay, that we have to decide. And the one thing that we may have to decide in some cases, depending on the question, is which is the major product that you get of all the products, okay, not just between the 2 products that you're getting for each carbocation, but for all the products you're getting. Okay, so here we actually have 4 products. We have 1, 2, 3, 4. Okay, so we have 4 products that are being formed here. So if you have 4 products, which one is going to be the major one? And the major is going to be 1. Why is that the major product? Well, first of all, your alkene is the most stable one, and the second of all, your ring is the most stable one. Okay, because cyclohexane is one of the most stable rings possible, even more than cycloheptane. Okay, so cyclohexane rings are going to be the most stable rings. All right, so then, which is the second one? Okay, so 1 is more stable or more major, if that's even something that we can say. Then the next one is going to be 4, because that is the Zide-Safe's product. And yes, you do have a cycloheptane, which is true, but you also have a Zide-Safe's product in there. Okay, and then the next one is going to be 2, and then the last one, the least product that you will form, is going to be 3. Okay, so that's your order from major to minor. Okay, and maybe 4 and 2 are competing with each other. We don't know until we actually do the reaction and then analyze the products, okay, that we have in there. But anyhow, I know it's a little bit messy, but I hope you understand how we do all of these rearrangements.